We're going to talk about perpendicular lines. This is going to be a lot of theorems. We'll go through them very quickly, give a brief nod to their proof, but not actually formally prove them. So perpendicular lines. First thing, let's look at this perpendicular, that might be perpendicular. Definitely it's a linear pair. We have an angle on the left, an angle on the right that form the red line. So this is a linear pair. These form a linear pair. They are supplementary. They add to 180 degrees. Okay, well, that would still be a linear pair that adds to 180 degrees. That would still be a linear pair that adds to 180 degrees, supplementary. But let's look at that one. What if that one equals that one? Okay, it adds to 180. Left equals right. So I could say that's the same as two lefts. I could divide them both by 2. 180 divided by 2 is 90. That means that's a 90-degree angle, and that's a congruent 90-degree angle. In other words, the lines are perpendicular. If lines meet to form a congruent pair, they are perpendicular. Another circumstance, here we have a line and an intersection. And let's say this is perpendicular. Well, perpendicular means it has a right angle. They meet at 90 degrees. Well, this and this are a linear pair, and they're supplementary, and they add to 180. 180 minus 90 here is 90 left over here. We could do the same thing to find this one 90, the same thing to find this one 90. And eventually we find the completely obvious perpendicular lines meet to form 4 right angles. Let's look at some angles here. Okay, I've got me a blue angle. I've got me a red angle. Let's say that the exterior and then they are adjacent angles sharing a vertex and a side. So these are adjacent, and the non-adjacent sides, the outside ones, form a 90-degree angle, are perpendicular. Okay? I said it wrong. The non-adjacent sides are perpendicular is what we're given. That they're perpendicular means that they are complementary. How does that work? Well, perpendicular means 90 degrees. The two angles being adjacent, you can find the sum of their angles, and it will be 90 degrees. Again, wholly obvious, but nevertheless, we're going tacky little, picky little step by tiny, tiny little baby step, and we have now that if the outsides of two adjacent angles are perpendicular, then the angles themselves are complementary, that they add to 90 degrees. We got 2 red lines here, 2 red lines. Let's say that the blue transversal. Now I know it is given to me that that little one right there, that angle, is perpendicular. These two are perpendicular. The blue is perpendicular to the top red one. But I know that the red one and the red one are parallel. So the blue and the top one are perpendicular. The 2 reds are parallel. What does that mean about the blue and the bottom red? You're right. It means that they are also perpendicular. How would I get that? Let me think. Okay, so here are 2 lines that are given as parallel, and here is a transversal. I know that this angle is 90. Well, let's look down here. Think of it as in a frame, lower right, in a frame, lower right. Oh my goodness, they're corresponding angles. The corresponding angles are congruent. The top red-blue angle is 90. The bottom one is 90. Therefore, the blue line is also perpendicular to the bottom red line. Okay, well, what about this? It's not really a converse, but it's kind of like a converse. So here I have 2 lines And they're just plain old lines. I don't know anything special about them. They're just, they're just lines. What I do know about them, however, is their relationship to the blue line. I know that this angle right here is perpendicular, that these two lines are perpendicular 90 degrees at this intersection. And I know that, so for the right one, the right red one is perpendicular to the blue line, and I also know that the left red one is perpendicular to the blue line. What does that say about the two red lines? Yes, you have it. They are indeed parallel. Since they're perpendicular, it meets to form 4 right angles, so this angle is 90 degrees. Same deal here, this angle is 90 degrees. Put them in a frame, they're both lower right. They are corresponding angles, they are congruent. Therefore, by the converse of the corresponding angles theorem, the lines are parallel. You'll recall that all those theorems that we learned a while ago, not very long ago, the straight on one starts with the lines being parallel and then goes to the angle relationships. The converses go from the angle relationships to the lines being parallel, which is the case here. Okay, let's talk about distance. Distance. Let's say I've got a line, and this line is Glenmont, the street right out here. Right here is the Subway across the street, and I'd like a sandwich. A meatball sub sounds really good. And then I'm like here, and I'd like to know how far it is between me and the Subway. I want to know the distance to the Subway. Or I guess more accurately, I'd like to know the distance to the street that the Subway's on. So I can start out here and I say, I'm going to go to the Subway. This is me. And here's the Subway. Nice sandwich. Yum, yum. Okay, so I could start out here and go over to the HCC, go behind them, go up in the parking garage, come back down, walk through Home Depot, and then eventually get to the street where the Subway is. I'm thinking that's not the shortest distance. What are you thinking? Between me and the street that Subway's on, which is Pin Oak Park? No. If I count all of this distance and how many steps I take and how long it takes me to get there, no, that will not be the shortest distance between me and the street that Subway's on. What's the shortest distance between me and the street that Subway's on? It's right there. Okay, when I look at that little piece of a line there, I wonder if it's perpendicular. If I take and try the same deal here, there's one that's the same length. I think it's the shortest. What if I move it out like this? Oh, well, it takes longer to get there if I go sideways like that. Now, obviously, this orange thing over to HCC and behind and all that is a lot longer. But notice this distance, if I put the same distance here, if it's not perpendicular, then it doesn't reach. If I'm not going straight over to the street that the Subway's on, then I'm not going to get there. I'm only going to get that far. I'm only going to get that far. The shortest distance is intuitively the perpendicular one. So that's just kind of a gut reaction on being short. We're going to have a few equations that we'll use. We can use them even though we don't really know that much about them. So at this stage in our mathematical career, we're just going to use them. So I'm going to give them to you. It's kind of like driving a car. You don't really have to know how all the things work. You can still push the buttons, push the pedals, and make it go. So for the purposes of this course, what we'll do is talk about how to get distance and we'll use formulas that are established that we probably won't learn how to do officially until calculus. So please make a note of each one of these. The distance from a point to a line is always perpendicular. If it's a simple one, you can always use the Pythagorean Theorem, a squared plus b squared equals c squared. If it's appropriate, it's the simplest way to do it. Otherwise, these two equations, which we're not going to really get into the derivation of, would be the way that you would find the distance. Okay? So, notice that for this one that's green, it's where the point, you have the point, which is xy, and the line is in standard form, which you will recall as ax plus by equals c. So that's when this one would be useful. You can also find out the distance between parallel lines, again, still perpendicular, but between them, when both of the lines are in slope-intercept form. So in this case, the slope, of course, is the same because they're parallel, and these are the two y-intercepts. You can use those elements of them to find out the distance between them. So if you're going through a handy-dandy little stream here, and you want to get to the other side, which is the shortest way? The way that's perpendicular to the side, of course. And here endeth the lesson.